Hi there. Thanks for joining us again. This is a Q&A edition of Space Nuts, where we take audience questions and we pretend that we know what we're talking about in attempting to answer them. Or we get it right sometimes too. Today, we're going to be answering a question about the temperature of black holes. I'm not sure we've been there before. It may have come up, but I can't remember when. And a question asking, with the James Webb Space Telescope and the Vera Rubin telescope, how much of the universe has been mapped? I can tell you, this much. And the emptiness of space is being questioned, and what difference will it make to humanity if we find dark matter and dark energy? That's a really interesting question, and Fred knows the answer. We'll ask him shortly on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back, and he has all the answers to all the questions of life, the universe, and everything. Professor Fred Watson, astronomer at large. Hello, Fred.
No pressure there, Andrew.
None at all. None at
No
all.
pressure, that's right.
Let's get straight into it, shall we? One of our regular contributors is Casey, who has a very interesting question about a subject we never discuss, black holes.
Hi guys, this is Casey from Colorado, and I was thinking about the temperature of black holes. I know that the accretion disk would be very hot, but I was wondering, once you get past the event horizon, if it would be hot or cold. Why do we think this? Thanks for the podcast, and I hope you're both well. Thanks.
Thank you, Casey. She's got me thinking about the temperature in Colorado because, we're facing some horrific temperatures around here at the moment, but I'd imagine it'd be quite the opposite in Colorado this time of the year.
Yeah, I think that's absolutely right, yes. Chilly part of the world in winter.
Absolutely. Now, temperature of black holes. This one's interesting because I suppose it varies on several factors. Where you are, what you're doing. I don't know what. I would it's not like the temperature of the sun, is it?
No, it's not. I'm so glad Casey asked this question because it sent me down a rabbit hole that I haven't been down before.
Oh wow!
And it leads you straight to quantum theory, it's. It really, in a sense, it's quite unexpected what's happening. So the bottom line is, whilst exactly as Casey says, the accretion disk of the black hole is extremely hot, and we're talking millions of degrees there because that's where you get X-ray radiation from. It's the stuff charging around the accretion disk that's swirling around the black hole itself. But the black hole itself is the opposite. It's really, really cold. And basically, it's because the amount of radiation that they release is at a level which means its temperature is measured in gazillionths of a degree. It's virtually absolute zero. It's quite a nice way of putting it, which I've summarized. I think this comes from Wikipedia. It may come from AI, actually. But the bottom line is, even though black holes pull in matter and energy, their temperature is incredibly low because their large mass makes their event horizons effectively cold thermal emitters, absorbing energy faster than they radiate it at these scales. So that's the key to what's happening, that like everything else, black holes suck stuff in. And that stuff is matter, which is equivalent to energy. And because it's stuff that's going in and not radiating outwards, even though there is what we call Hawking radiation, which I'll get to in a second. But what it means is that the fact that there's an energy input into the black hole, it means that to the outside observer, they look cold. They look very, very cold. There is a relationship, as you said, it might vary with some things. And what it varies with is actually the mass of the black hole. It's roughly an inverse proportionality. The temperature is inversely proportional to the mass. And what that means is for supermassive black holes, they are extremely cold. And that sort of figures because they're sucking in more energy. And so the surface to an outside observer would look colder. They're talking about 10 to the minus 14 degrees Kelvin. Something with the mass of the sun is a balmy 10 to the minus 7 degrees Kelvin. It's still virtually zero, but it's more than the supermassive black holes, so something with the mass of the sun. So it's inversely proportional to the mass, that inverse relationship. So that's kind of what... It's the Hawking radiation that gives the black hole a temperature, essentially. It's because it's emitting radiation. And we've talked about Hawking radiation before. Even though everything gets sucked into a black hole, there's this quantum situation where you can get two virtual particles being created from nothing in empty space. One gets trapped by the black hole, the other doesn't. And so we see that as Hawking radiation. Suggested by Stephen Hawking in the 1970s, now very well established. But yeah, to summarize, the bottom line is Casey's question is a good one because it turns out that black holes are very, very cold indeed, despite the intense heat of the accretion disk. Work that one out. It's a really hard thing to put your imagination around.
I suppose you'd compare it to the heat on it's got nothing to do with it at all, but by example, the heat on the sunward side of Mercury versus the cool on the shadow side. They're so extreme.
Yes. Yeah,
but
that's right.
Not for the same reason.
Well, it's similar because the dark side of Mercury is cold because it's radiating energy into space. Whereas, and that energy loss reduces the temperature. Whereas with a black hole, it's the other way around. The thing is sucking energy in at a greater rate than it's emitting energy. Mercury's dark side would lose heat by infrared radiation. That radiation, in the case of a black hole, is much smaller than the radiation that it's sucking in, which is why it looks extremely cold. So I'm trying to make sense of the parallel that you drew, and I think it holds water, Andrew. I think it's a good answer.
Well, actually, the water would probably evaporate or freeze, but anyway,
freeze. Yeah.
I just thought of a question. So if a black hole sort of, runs out of food, would that cause an alteration in its temperature?
I don't think so, because I think once I get what you're saying, and certainly in the argument that we've just been talking about, you'd think that if it's not sucking in energy anymore, or sucking in matter anymore, it would actually change its temperature. The reason why I think that might not happen is because the only thing that the temperature seems to be related to is the mass itself. So there must be a mechanism, and I'm sorry it's eluding me at the moment, but there must be a mechanism that sort of locks once you've got a black hole of sufficient mass. Then its temperature is sort of locked in. It must still be taking in energy in the form of radiation, so perhaps that's what's happening. Light certainly gets sucked into a black hole, even if it's not got an accretion disk of stuff to feed on. The light's certainly going in, and perhaps that's enough to keep the temperature as low as we've described.
Indeed. All right. Thanks, Casey. Lovely to hear from you. Hope you're coping with the minus 10 to the 15 degrees Kelvin in Colorado. Our next question comes from Eli. Hello, Spacefarers. I'm writing from the Coachella Valley Desert here in Southern California. I've often thought some of the Google Earth-like software would be amazing to take into other galaxies throughout the universe. Intriguingly, I imagine you could take them back in time according to estimates of cosmic inflation, etc., all the way to the Big Bang, in theory. To his question, with James Webb and the Vera Rubin coming online, how much of the visible universe have we basically mapped, and how much are we projected to map in, say, the next decade? I think we've actually talked about how much that they're going to look at and how long it's going to take. And I think Eli's going to be quite surprised by the answer.
Well, yes, that's right. I mean, the key words here are the Vera Rubin Observatory, because that will map the entire sky down to quite a significant depth, not as deep as the Webb will, although it is an 8-meter telescope. The Webb is only 6.5 meters, so it's probably not far short of it. The Webb, of course, looking in infrared, and the Vera Rubin telescope looking in visible light. But it's gonna photograph the whole sky, southern sky, in every three nights or so. So that will build up over the years a map of the things that don't change. I mean, what it's looking for is things that do change. But as you integrate for all that time, and by that I mean you expose the detector to the sky so that you build up the image, and you can add all those images together. We'll have almost a complete map of the universe in the southern hemisphere, because all the visible galaxies will show up. We won't see the first galaxies. I don't think it's going to be powerful enough to see those, but and we're not sure even that the Webb has seen the first galaxies. It's certainly seen some galaxies that we think are very early in the history of the universe, and I think the Vera C. Rubin Observatory will do the same thing. But so we're not in any sense getting a complete sense of the a complete census of the universe, but it's not going to be far off. And that's quite astonishing when you think of where we were, just a few years ago. Certainly when I was a young working astronomer in the 1970s, I would have had it would have blown my mind to think that we could map all the galaxies in one hemisphere of the universe.
Yeah. What about the northern hemisphere? Is there any work
there's
going
no
into that?
equivalent. There is. The Nancy Roman Space Telescope will look. It's also a wide-angle telescope, like the Vera Rubin Observatory instrument is, but it's not as big. It is a 2.3 meter telescope. It's basically a Hubble telescope, but with a wide field of view. So we'll certainly see pretty deep into the northern hemisphere. Whether it will go as deep as the Rubin Observatory, it's a different matter. I don't think it will, because it's a much smaller telescope. But it is in space, and that gives it, that gives it advantages. There's no atmosphere to get in the way. So that's perhaps the best bet. The other big instruments. I mean, there's a number of things going on in terms of the two Keck telescopes, which are in the northern hemisphere in Hawaii. They're 8-meter class telescopes, but they're not wide angle. These are telescopes that are built to home in detail on individual objects rather than to do wide angle surveys. You need a specially designed telescope for that, and the Rubin is exactly that. There isn't really an equivalent. There is a wide-angle telescope in La Palma, which is basically the same as our UK Schmidt telescope here in Australia. It's called the Ocean Schmidt telescope. It's much older than our Schmidt. In fact, our Schmidt was modelled on it. And that's a wide-angle telescope that's surveying the sky, but that's looking for things like near-Earth asteroids and things of that sort, rather than penetrating deep into the universe, because it's only got a 1.2 meter aperture diameter. much smaller than the 8 meters that the Rubin telescope will have.
Yeah. Still, what we'll know in 10 years' time will be extraordinary through these two telescopes alone, James Webb and Vera Rubin. Who knows what they're going to unveil and what Vera Rubin's first photograph was a revelation, and what James Webb is shelling out is extraordinary. It's like I don't know, Taylor Swift. It's a hit record every time they release a picture. It's incredible. So Eli, the next decade will be extraordinary. So just keep an eye on it would be my advice. And thanks for the question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a break from the show to tell you about our sponsor, NordVPN. Now, if you've ever felt like your online privacy is slipping through the cracks, then you're not alone. Hackers, scammers, harvesters, they're all out there trying to get your private info, whether that's your passwords or your personal details to sell on the dark web or to use themselves to access your bank accounts, credit card details, and who knows what else. But you can protect yourself with NordVPN. You can take control at home, or more importantly, when you're out in public using free Wi-Fi. Right now, using the exclusive Space Nuts offer, you can secure and receive 4 extra months for free on a NordVPN.com plan. That's over 2 years of top-tier online protection. NordVPN encrypts your internet connection, hides your IP address, and offers access to over 7,700 servers around the world. Plus, with features like Threat Protection Pro, MeshNet, ultra-fast speeds via NordLinks, your digital life stays private and efficient. So don't miss out. Visit nordvpn.com/spacenuts and enter the code SpaceNuts to claim this deal. Remember, there's a 30-day money-back guarantee, so it's risk-free to try. Stay safe, stay private, and browse with confidence. That's nordvpn.com/spacenuts and use the code word SpaceNuts. nordvpn.com/spacenuts.
3, 2, 1.
Space Nuts.
I think we have an audio question now. This one comes from one of our regulars as well.
Hello, Fred, Andrew, Jonty, and Heidi. This is Robert from the Netherlands. I have a question for you guys about the emptiness of space. Now, everybody is always saying that space is totally empty, right? 1 proton per square meter, something like that. However, not that long ago, scientists did discover the Higgs boson particle, the God particle, if you will. So apparently everything is on this grid of Higgs bosons. But I'm not exactly an expert here. I'm just curious if you guys could shed some lights on this concept for me. So is it just an enormous field of these very regular Higgs bosons everywhere, and that's what space is, or are they more numerous or less dense in certain parts? Is the void between galaxies actually a void, or is it an empty field of God particles? I really hope you can shed some light. Thank you guys so much for answering.
Thank you, Robert. Good to hear from you. The emptiness of space. So he said 1 proton per square meter. Is that a reasonable formula?
Yeah, it's per cubic meter, something like meter. That. It's of that order, I think, in intergalactic space. But Robert's right in the sense that the Higgs field, which is the other way of looking at the Higgs boson, permeates empty space. So this is all about the duality of particles with waves and with what we call fields. And I mean, we imagine fields when we think of gravitation, because we think of a gravitational field as a sort of a well, if I can put it that way, in a trampoline. The trampoline's the field. You put something in it, and it distorts it.
Yep.
So with the Higgs boson, the Higgs field is this sort of invisible. It's been described as something like molasses or syrup that what actually give particles their mass, because they move slowly through it because they get sticky. That's one way of looking at it. But the Higgs boson is essentially in a sense a ripple in the Higgs field. The Higgs field fills space, and the Higgs bosons are ripples in it. That's one way to look at it. I think what Robert's interested in is the density of these bosons, whether they are uniformly distributed through space, or whether we're talking about, bosons that are more dense in some places than others, and I guess the bottom line is that you would expect there to be more bosons where there is more what you might call normal matter, the quarks and normal particles. But that might not be the case. I need to look at that a little bit more carefully, Andrew, as you can probably tell, to find out what the distribution of Higgs bosons are. If you assume the Higgs field is uniform throughout space, which I think it might be.
Yeah, I suppose so. I mean, it's a complicated area. You're talking about particle physics, aren't you, really? It's, it's not...
I believe so, yes.
It's not basic maths. So,
yeah, it's particle physics we're talking about. And as I've said before, the disclaimer is I'm not a particle physicist. I've been to CERN a few times and had my mind blown by what they do there at the Large Hadron Collider. In fact, I've been underground in the Large Hadron Collider, but I'm still not a particle physicist. I learn what they tell me and kind of hope for the best.
Yeah. Aren't they making a larger Hadron Collider?
They are planning one, something called... I can't remember. It's something like the Future Large Collider. I think it's something like that. Right. Whereas the Large Hadron Collider has a diameter or a circumference of 27 kilometers. This is 100 kilometers. If they ever get the money for it, they are planning an opening ceremony for it in 2070.
It's called the Future Circular Collider.
Future Circular Collider, that's it.
91 kilometre ring successor to the Large Hadron Collider. And they expect it to be approved in the 27-28 financial year by the look of it, construction starting in the 2030s. So it's a little way off.
Completion in 2070.
2070.
Yep. That's when the last.
That's not hold our breath, Fred.
Is what I saw. Yeah. So I don't think even with the best will in the world, Space Nuts will probably have dwindled to an audience measured in single digits by then. So
possibly so. Yes. Well, we could pick up new listeners along the way, but we won't know about it. But I suppose the other side to this question, though, is that we do see concentrations of particles in some parts of the universe, like dark matter seems to concentrate around galaxies, kind of thing. Is that that a different kettle of fish?
I think so, because we're talking about something that is a property of the universe itself, almost. So that the Higgs field is everywhere.
Okay, gotcha. I understand. No, I get it. Yeah, all right.
Yeah.
So, Robert, the answer is maybe, possibly, could be. We need to do a bit more homework by the sound of it. We might be able to get back to you on that. Just Fred's writing a note so he doesn't forget. Except he'll forget where the note is. Shh.
All right. It's in this book.
Thanks, Robert.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
And our final question comes from Rennie. This is a really interesting question because he says, I'm going to play devil's advocate with this question. How will finding out what dark matter and dark energy really are help the Earth and all of its life now and in the future? Rennie from California. We've had a few US questions this week. It's nice. 2 from Callie. What difference will it make if we find this stuff to Earth and life as it is now and in the future?
If we magically did find the answer to these things, and we will eventually over a period of time. I hope it's I hope it's before 2070 because I want to know. What it will do will be complete our understanding of the universe in a way that it is not the case at the moment. So it basically refines our understanding. If I can put it this way, in a way that's similar to the way general relativity refined it back in 1915. So the fact that we suddenly understood gravity, or the way gravity works, in a new light, which is what general relativity did, meant that yes, the physicists could go away happy because they'd solved a problem. There were a number of problems that Newtonian gravity couldn't help with, which were solved by Einsteinian gravity. So, but that didn't seem to offer any future benefits for humankind. But here we are, rather more than 100 years later, 110 years later, and we have tools which rely absolutely on general relativity. And the one I'm thinking of most commonly is GPS, because our position finding software simply would not work without general relativity. You'd have errors in the region of 10 kilometers, which is not kind of what you want with GPS. But that took 100 years. Yeah. And so, Rennie, that's the sort of timescale, I think, on which you have to be optimistic about the way it might help humankind or life on Earth generally. Because if we become a responsible species on our planet, we're going to help the whole planet if we live sustainably and live alongside all our companion organisms on this planet. So, I think what you can't say is that it won't help them. That's the thing. You can't say that it will either, but there's a good chance that in the same way that something as abstruse as general relativity actually comes into everybody's everyday life 100 odd years later, I think that's the model. And it's one reason why deep research like this is funded. It's why fundamental research that is just knowledge for its own sake at the moment, why it's funded, because you never know what the spin-offs might be.
Absolutely. And you can look back in history at some of the great discoveries and how they've changed things on Earth and have changed human life. I'm just trying to think of one.
Well, electricity for a start.
Yeah, well,
it was just physicists playing around in the early 19th century. Oh, this is really interesting. Nobody ever thought we'd use it like we do today.
And I suppose one of this is probably a fundamental example. As we learn things, So it expands our minds, it expands our inquisitiveness, it expands our intelligence. It enables humanity to understand more about itself and its place in the universe. You go back to 1543 when Copernicus found that the Earth was not the center of the universe. I think he got shouted down pretty heavily for that, but that's the truth. We know that now. There was I can't remember who it was, but another thing that goes back quite a way when the discovery was made that our sun is actually a star. I mean, for a long time, we didn't know that. You know, it's about knowledge as much as anything, I think.
Yeah. Yep.
I love that one, though.
That's right. Yeah. It's
about the sun.
It's great.
Yeah.
I think
you can look it up. It's online somewhere. I did it as a quiz question once on the radio and got a great response to that because people just, in the modern era, never thought that there would have been a time where people look at this hot ball in the sky and go, what is that? And, you know, looking at all the other stars, not making the correlation. They just didn't know. It was incredible. So I suppose, Rennie, it's about knowledge. It's about expanding our understanding of life, the universe, and everything, and not stopping at 42. That's the way I look at it.
I think you're absolutely right. I think both. That's two sides of the same thing. But it's why we do this sort of thing. We're a curious species, and
absolutely
knowledge is power. Yeah.
Yeah. Yeah, that's another thing. Yeah, absolutely true. Rennie, great question. Good one for discussion and debate, and keep them coming. If you'd like to send questions into us, you can do so through our website, spacenutspodcast.com, spacenuts.io. They're the two URLs. And while you're there, have a look around. The AMA button at the top, Ask Me Anything, is where you send your questions. Ask me anything, text or audio. Don't forget to tell us who you are and where you're from. And you might want to click on the Support Our Podcast button and help us out if you so desire. Never, ever going to make it mandatory, but there are advantages to becoming a supporter of the podcast. So check that out as well and visit the shop while you're there. That also helps us. Buy a sticker, buy a cap, buy a shirt, buy whatever. We should have Space Nuts sunscreen, you know? It would make sense. Anyway, you can do it all on our website. Fred, thank you so much. Always a pleasure.
Good to talk, Andrew, and I'm sure we'll do it again soon.
Yes, I'm sure we will. Could be a few minutes, could be a week, who knows. And Hugh in the studio, thanks to him for doing everything he does. We don't know what that is, but we appreciate it. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.